And welcome back to part 2 of our look at functional reactive programming through the game Cuboid. I'm glad you made it to part 2 because in part 1 we were really just getting warmed up. We haven't yet worked with graphics or OpenGL, and for all our talk about functional reactive programming, the ball in our program wasn't really reacting to anything except for time or gravity. In this video, we're going to take what we have and extend it a little bit further and end up with something like this, where we have an animation of the ball falling and reacting to the floor, which is invisible here. Rather than continue working with just numbers printed at the console, let's go ahead and visualize the ball with OpenGL. We could start from scratch and go through implementing this, but this isn't really a video about OpenGL, and we might as well use the code inside of Cuboid to get a jump start on things. Sort of how we utilized some of the parsers from Parsec to build a simple email validation program. So let's switch over to graphics.hs from Cuboid. We briefly looked at this before, but what I'm interested in here is, first of all, this initGL function. In our main, in Reactimate, in the init function, we're not doing anything. What we could do is initialize OpenGL here. And instead of the window being called Cuboid, let's call it Bounce. And we'll just stick to that for now and see how it works. The next thing we need to do is initGL has this reshape callback, which gets called when the window is resized, and actually when the window is first created. It says here that it just copied the code from reactive glut. We'll copy the code from it. And then finally, there is this render game function, which if we look at it, is doing the job of rendering the state of the game to the screen. You can see that it's taking the game state as input, and these render functions here are drawing things out. There's also this draw function, which is actually a signal function that calls render game. So let's go ahead and grab all of this and place it into our main. So now what we want to do is, instead of just printing this out, we'll keep the printout to the console, but we also want to draw the ball. We don't need draw to actually be a signal function because the signal function has already been run by Reactimate and we get a value out of it. So let's just pretend we have something that uses position. And in fact, we don't need this. We can take this single statement here, clear, add it to render game, and there's already a flush here, and so we'll just rename render game to draw. We don't have a game state, we actually have a position, so let's change that as well. And we also don't have to worry about the rotation of the cube, lighting, anything else, the wireframe, and so on. The goal, all of the obstacles in the level. We're just going to focus on using the red sphere that represents the player. That's going to be the sphere that we're dropping, or the ball that we're dropping in our scene. Now, render player here sets the color to red and then renders a shape, in this case a sphere, at a position. And the position here is P, and the important thing to note here is that even though there's no type annotation on this helper function, it's a vector 3. You can see it taking out the x, y, and z components here. So we'll use Yampa's vector 3 and give it a, just going to give it this position based on testing. We'll actually see the ball coming through and the position. So this is the x, y, and z of the ball. We've only been calculating the y, but we need an x and z for OpenGL. So let's go ahead and see if that's enough for us to get a working demo. And we have a lot of undefined or not in scope stuff here. So let's take a look at the imports we need. Let's pull these imports and see if we get any closer. And we're missing type constructor class R, which there is a types module here, and R is an alias for GLW. I'm sorry, GL double, which we can just define ourselves. And there's also not in scope size, which if we look in utils, size takes a level and returns an integer. And the size is actually the maximum number of the coordinates of the obstacles. So to see what that is, we can look at the levels. These are how the levels are defined in Cuboid, and they are points in 3D space. The first being the player, the second being the goal, and the third being a list of obstacles, those cubes that the player ball can rest on. So just glancing at this, you can see that the size of most levels is going to be 5, and then we have this +1. So let's go ahead and just change any instance of size L with 6. And then try this again. And now we have a mismatch between our position and this GL double that we were looking at here, this R value. So far we've been working with double. There's a different type of double that's defined by OpenGL that Cuboid works with, but they should both be doubles. They should be compatible, so we'll use unsafe coerce. And I'm not too concerned about it because this is just a demo after all. So let's believe that's part of unsafe coerce. And let's try that again. And it compiled. So let's see what it actually does when we run it. Bounce. Oh, and you can see that we just caught a glimpse of the ball, and I'm not actually able to kill this window normally, so I'm going to have to kill it from another terminal. And in order to save us some time in this episode, I'm going to explain what's happening here. We're using Reactimate, which is sort of an event loop, but OpenGL has a loop that it requires called the main loop, which you can see here. And without the main loop, the resize, callback, and the keyboard events won't work in the program. So what Cuboid is doing here is, instead of using Reactimate, it's using a combination of React init and, in OpenGL's idle callback, React as an alternative. So instead of allowing Yampa to do the handling of time and events, it's doing so with OpenGL and then calling Yampa with events as it receives them. There's a little bit more to explain about what's going on here, but let's go ahead and just grab all of this and pull it into our program. And we'll comment out the main we wrote before and see if we can rework this into what we need. So let's briefly look at main. First, a couple I/O references are set up. And if you haven't seen I/O references before, they work like variables in an imperative programming language, but they're only usable in the I/O monad. First, a reference is set up for input, which we're not going to worry about right now, so we'll comment that out. Then one set up to store the time. Here, React init is called with initgl, which is what we want, but it also returns no event. And that has to do with how Cuboid is handling input. But since we're not dealing with input, we'll also comment this out. And finally, as with Reactimate, there is a main signal function. Again, since we're not dealing with input right now, we're going to comment out the keyboard and mouse callback, and then we can look at the idle callback. The idle callback is called by OpenGL when it decides that we can go ahead and do some processing. And Cuboid uses it to actually do drawing, which I'm not sure is the proper use of it, but it works. But first, let's comment out this new input. We're not going to be using input, and we'll comment it out here as well. And in the React handle. And finally as the argument here. And here. And there's one more place we're not looking at input, and that is here. We're just going to return nothing. And so what idle is doing here is it's called with the old time, the last time it was called. It figures out the elapsed time between the last callback and this one, calculates the dt, or the time differential, or delta, and then calls react. In the case of Cuboid, it calls react with input from the user, or the keyboard and mouse callback. But again, since we're not dealing with the input from the user yet, we're just going to call it with nothing. And then at the very end, it writes out the IO reference for the old time with the value from the new time. So you can think of this as what we were doing earlier with the thread delay of 1/10 of a second and returning 0.1 and nothing. Just in this case, it's not a regular amount of time that's passing. It's whenever OpenGL decides to call our idle callback. So we need to calculate the time that has elapsed each time. Finally, let's look at this main signal function here. We're not going to use parse, input, or update. Those are part of the game that we haven't covered yet. But our main signal function up till now was falling ball 10.0. So falling ball 10.0. And draw is not a signal function. It's a standard function in the IO monad. So let's go ahead and change it to take as input the position and velocity. I'm going to draw the position, and we want to pull out, for now, we're going to continue writing out the information to the screen. So we'll put that in here and draw the position. So let's see how that compiles. And we're missing IO ref, which is part of data.io ref. And it compiled, so let's take a look. And we don't see anything, but we are able to terminate the window, so that's a good sign. And based on some testing, let's reposition where this is falling. Let's move it back on the z-axis about 30 units and try it again. Oops. We don't want to, we want that to be a single argument. And let's take a look. And that was very quick. Let's take a look one more time. And the ball is falling so rapidly that we can't see it. And the reason for this is here in the calculation of dt. I'm not sure why this is the way it is, and we might take a look at this when we analyze the code for Cuboid in more detail. But the units that we receive from get elapsed time is in milliseconds. So this should really be divided by 1,000. And we can remove that. And let's try that. Okay, that looks a lot better. So we're making good progress. We have a visualization of the ball falling that's a lot more pleasant to look at than those numbers on the console. But the ball's still not bouncing. And So let's see what we can do about that. We'll start by creating a new signal function, bouncing ball. And it's going to have the same type signature as the other signal function because we still need to do the same work with it. And now what we want to do is take the output from falling ball, and we need to test to see if y0 has reached 0 or the floor. And one way to do that is with the edge function. Here, I'll write it this way. And the edge signal function is a signal function, we'll just write it out here, a signal function that takes a Boolean value and then returns an event. Why we want to use this won't be clear until we take a look at switches. So let's do that now. Looking at the Yampa page of the Haskell wiki, you can see some interesting diagrams that may help you visualize what's been going on so far with arrows. Remember the triple ampersand operator? Here's a diagram that might make it easier to remember or see what's going on. But what we're interested right now is in switch. And let me reduce the zoom level here. A switch really looks like a switch in a circuit diagram for electronics. And what it allows us to do is switch between signal functions. So to begin with, we have a signal function for falling ball. And conceptually, what we want to do is once the ball has hit the ground, we want to switch to a signal function for the bounce upwards of the ball. But before we do that, let's take a quick look at the type signature, and I'll zoom in again, for switch. And it's a little bit weird. It takes a signal function of an input with an output that's a pair of an output and an event. Then it takes a function that takes the value of that event and returns a signal function, and finally returns a signal function. So the way to think about this is we have a signal function, and that signal function may trigger an event at some point, which switches us over to a different signal function. And this is where the reaction in functional reactive programming comes in. Up until now, we haven't really been reacting to anything. I mean, the ball's been reacting to gravity or time, if you want to think about it that way. But it hasn't reacted to input from the user or the environment, and now we're going to have it react to the ground, or position 0. Now, edge is a signal function that takes a Boolean, so we actually need to give it a Boolean value that tells it when to fire, and we can do that by taking a pure function, which we could use array to lift, or we could do it like this, where we receive an output that's a position and a velocity, and we test it against 0. So let's do a comparison. Position is less than or equal to 0 because it may have already passed 0. We don't need this type annotation. And we're going to have to use switch here at some point. But we're going to pretty quickly get to a point where this gets really hairy trying to do this in point-free style. And this is where arrow notation comes in. So arrow notation is similar to monad notation. Whereas monad notation is a do block with values set with an arrow, or rather an assignment operator here. An arrow notation block starts with keyword proc, followed by the input for the signal function, which is just going to be nothing here, but we'll go ahead and name it anyway. And then a do block, just like a monad do block. So now we can write like this. We have our falling ball signal function, and it takes its input on the right and produces its output on the left here. Now that output is named in a way that we can use, just like in a monad block. So for the edge arrow, we can pass it in this Boolean value, this comparison here, and it will return an event. Finally, just like a monad block, there's return, but it's called return A, and we write it with this arrow operator. And we return the value we want to return. But let's recall the type signature of switch here. It takes a signal function with an input, and the output is a pair of the output we want and the event. So what we're really going to be returning is this. So this looks great and all, but where does the switch come in? Right now, the way that we've written this, the type would be actually something like this. And that's not what we want. We want to keep the type the same because the react function needs to just receive a position and velocity. So we need to do the switching inside of this function. So let's use a where, and we'll just call this BB. Change this here since I don't like shadowing variables. And now to get the right type, we'll use switch, and we'll switch on this signal function we've defined below. And we're going to have to switch into a new signal function. So again, to review what's happening here, because I know it might be a little bit hard to follow. First, Yampa is going to use this signal function we've defined here, which is really just the falling ball signal function that detects when the position has reached 0. When the position reaches 0, an event is fired, which will tell switch to switch to a new signal function. So what should that signal function be? Well, if you remember from the slide, what we want is a fully elastic collision, where we keep the position of the ball, but we invert its velocity. And by doing so, we give it an upward velocity equivalent to the downward velocity it had when it hit the ground. To do that, we could define a separate signal function, but it turns out that the falling ball signal function does exactly what we need. We just need a way to set the velocity on it. And we can do that by giving it a velocity parameter, v0, which you might remember from the slide as well, which we hadn't used up till now. And while we're here, let's go ahead and switch this over to arrow notation as well. And I'll name the input even though we don't use it here. And now we write this like this. Our velocity is going to be the integral of negative 9.81. And that's this term right here. And the position is going to be the integral of the velocity, but we're also going to add the initial position. Now, depending on how you think about things, this may be a lot easier to read than what we had before. I know it is for me. There's one more thing we need to do, and that's that we added this initial velocity, so we need to do the same thing with it. We need to work with the initial velocity. Because for bouncing ball, we're going to be switching in a new signal function where the starting velocity is not 0, it's actually a positive value. Oh, and we need to, of course, return what we want here, and that's the position and the velocity. So going back to bouncing ball, we need to add initial velocity here as well because of the way we're going to write this. And we'll add it here. So now we have an initial position and an initial velocity being passed through these signal functions. And what we're going to switch into is bouncing ball with an inverted velocity. To get that, one more time, let's look at switch, and the event, whatever value is passed in the event, gets passed to this function that determines our signal function. So to pass a value, we can use tag, and we're going to pass the position and the velocity. So here, we're going to receive the position and the velocity at the time that this event occurred, and we're going to switch to bouncing ball with the current position and the inverted velocity. Now that we have this written, let's switch our main signal function from falling ball to bouncing ball, and we need to give it an initial velocity of 0, and we should be ready. But first, let me fix this type signature back to what it should be. Okay, and compile. And we have a parse error on line 16. And that is because arrow notation is not standard Haskell. We need to set a language pragma for arrows. And we received another parse input on line 26. And I'm guessing this has to do with some sort of indentation problem, so let's move this over. And try again. And it compiled, so fingers crossed we're going to have a bouncing ball. And it worked. Now, I know this video is getting kind of long, but I want to do a couple more things that might help you see what switch is doing here. Instead of having a fully elastic collision, let's try using, let's try returning just 60% of the energy in the bounce. And see what that looks like. And now the ball bounces and comes to a rest. Actually, it didn't fully come to a rest, it broke through the ground. And what's probably happening there is a floating point error that allows it to reach some sort of escape velocity. So what we can do is test to see if the velocity, if the ball has slowed down enough that we can just switch into a different signal function that just returns a position 0 with velocity 0. So what will happen is once the ball has slowed down enough, instead of switching into a new bouncing ball signal function, we'll switch into a constant signal function. So let's take a look at that. Now, whoops, the ball has come to a rest immediately, and that is because a negative velocity is what it's going to have when it hits. We want the absolute value of the velocity. One more time, the ball bounces and then comes to rest. We've looked at a lot this episode, and if you're new to functional reactive programming and arrows, this may take a while to sink in. But I hope that we're all at least to the point where we'll be able to make some sense of the rest of Cuboid's source code, namely the code that manages the state and the updates in the game. We'll see how the environment of Cuboid reacts to input from the user, as well as items in the environment or shapes in the cube reacting to each other. So that and more on the next episode of Code Deconstructed. See you then.